So in the next homework, we're going to be calculating double integrals in volume, and I wanted to start with just some preliminary conversation where we look back at single variable calculus and what we know about it, and then extend those ideas to functions of two variables. So in Calc 1, we identified that when we calculate an integral, that we are finding the area under the curve, and that area might be assigned. It might be a signed area. And the idea was really simple. We have our x and y axes. And we have some curve f of x. Who knows what it looks like? It doesn't matter. And we integrate over some interval from a to b. So we integrate between a and b. And we take the function f of x and multiply it by dx. And what we want to recognize is that this is just a height times a width. These dx's came from us breaking the interval from a to b into n rectangles. Let me draw one of them. We break it into n rectangles. Let's draw one of them. And then what we did is we said that, hey, this rectangle here has width delta x, and this is the ith rectangle that we're working with. And then we said, hey, there's going to be, let's pick some number right in the center, and we'll call that number x of I, and we're going to multiply delta x of I times f of x of I. And what we recognize is that this is a height. The function gives us a height, or the y coordinate is a height, right? We have y equals f of x. The y's are heights. So this was a height times a width. And then what we did is we said, hey, we want to get this is an area, and this area either overestimates or underestimates the area under the curve. But what we did is we took the limit as all of the x of i's went to 0, and we added them all up. So we took the sum from I equals 1 to n of x of I times delta x of I, and we added up all of the areas, and we said, hey, this approximates the area. And then we identified a norm. I'll call it big N for norm. And the norm was the width of the widest rectangle that you have, and you take the limit as the size of that norm goes to 0. So you let these delta x of i's become dx's. And then we get the exact area under the curve, because this is infinitely thin. And when it's infinitely thin, the rectangle fits the curve exactly. So we calculated the area under the curve, and then we said, hey, we want to recognize that this curve might actually go below the x-axis. And if it does, we have a height times a width as an area. But down here, the heights are negative, so this area down here is a signed area, in the sense that it's a negative area and actually subtracts from positive area over here. So we identified that the area under the curve could be found by integrating, and then we also identified that if the x and the y axes are actually not x and y axes but have physical significance, so for example, if this axis is speed, let's say it's feet per second, and then over here we have a time axis in seconds, then we recognize that when we multiply height, which is measured in feet per second, times width, but the width wouldn't be a dx, it would be a dt. So when we take speed times time, height times width, speed times time, we got feet. And it turned out that the area under the curve actually had a physical significance. It represented the distance traveled, or feet. And letting dx or dt or whatever it is, letting that change go to 0, really what we're taking advantage of is the fact that by letting the delta x go to 0, no matter how curvy the function is, it's going to look flat to us as we zoom in on it. So for the same reason that, the Earth is round, but when we zoom in on the surface of the Earth locally, it looks flat. That's letting that change in x go to 0. So if you think about, think about it. Take and look at a parabola, which isn't a straight line, right? Not even close to a straight line. And so if you take a delta x right now on my x-axis, my tick marks are every 1. So if we think about the x-axis tick marks as being our delta x's, right now my delta x is equal to 1. And what you can see is your rectangle doesn't fit the curve very well, right? So you can estimate the area under the curve by that rectangle, but it's not a great estimation because my delta x is large. But think about what it means to let delta x go to 0. So if we let delta x go to 0, that's just changing. We can think of that as just changing the scaling of the x-axis. So make the tick marks smaller. So right now, for example, this guy right here, what does he say? He says this is 1.27 and this is 1.28. So now if I draw in my rectangle, it fits pretty well. And what's my delta x? My delta x is 0.01, which isn't 0, which isn't even close to the limit. Taking the limit as delta x goes to 0 means let delta x go to, let it get infinitely close to 0. But as you do that, as you let delta x go to 0, you're changing the scaling on the x-axis in a sense. So if you let the tick marks get smaller in size, in other words, you take that limit as delta x goes to 0. What's delta x right now? Delta x is, what is this, 1.29106, 1.29108. Right now my delta x, if I subtract this x coordinate minus this one, is going to be 0.00002. What happens to if you let that be your delta x, what happens to the left and the right side of that rectangle? Well, in the limit, they fit perfectly. So you do have the area of the rectangle exactly fitting the area under the curve. So when you take that integral from a to b, and you take the height times the width, but you've let delta x go to 0, so you're doing f of x, which is the height. That's the y coordinate on the function. That's the height. And you multiply by dx, you're getting the area. But the summation, the sum, right? This just means add all of them up. Add up all of those areas. Well, because now you have the rectangles exactly fitting the curve, you get the exact area under the curve. And that's the basic principle behind it, is that letting delta x go to 0, letting that delta x go to 0 means you're zooming in on a curved surface so close that it is locally flat. So this idea extends. Yes, I do want to exit ink to go. This idea is going to extend to double integrals. So with a double integral, you're going to get a volume instead of an area, and the reason is you're breaking a region R. So now we're not working with a line interval. You're breaking a region R in the x, y plane into infinitely many squares. You're constructing a grid in the xy plane, and this grid is going to have delta y's and delta x's. So delta x times delta y is going to be the area down here, and then up above it there's going to be a height. So we're going to take a double integral over a region, and then we're multiplying by dx dy or dy dx. This is just an area of a square in the xy plane, and then we're multiplying it by f of xy. This is going to be, right, z equals f of xy. This is a change in x times change in y is the area of a square in the xy plane times z, which is a height. The z coordinate's just the height. So you get length times width times height, length times width times height, and that is a volume. And you get the exact volume for the same reason that in single variable calculus you get the exact area. That's because we take the limit as all of the delta x's and all of the delta y's go to 0. And when we do that, just like when we zoomed in on a curve, it looks locally flat. When we zoom in on a surface, which might look curved here, but when we make these squares in the xy plane infinitely small in size, when you look up above it, what you see is a flat surface above it. Just like when you zoom in on the surface of the Earth, as a human, it appears locally flat. So you're going to get the volume under the surface, and that volume could be a signed volume depending on whether x, y, z are positive or negative. So another way of thinking about it, and this is a nice way to think about it, let's suppose you're doing dy dx over some region. So we have a function f of xy, and we're multiplying height times width times length. And let's say you're controlling things in the y direction with two functions. So it's going from h1, some function of x, some second function of x controlling the y direction, and then you're integrating in the x direction from a to b. So if you think about it, when you do this first integration and you're holding x constant for each constant x, so hold x constant, you are finding the area of a cross-sectional area, right? This integral here is just an integration with respect to one variable, which gives you an area under a curve. You get a cross-sectional area. You've held x, the x direction right here, you hold it constant. Hold x constant and integrate means you're finding the cross-sectional area. And then once you find that cross-sectional area, what do? You multiply it by dx, which is just the width right here. This is dx. So it's cross-sectional area times width still gives you a volume, and this is a double summation. So this says add up all the cross-sectional areas, multiply them all by the width of each cross-sectional area, which is a volume, add up the outer integral, add up all of those volumes, f of x dy cross-sectional area times dx. So that's the basic idea. When we integrate under a surface, we're getting a volume, and the volume, depending on your location, could be a signed volume. And just like with single variable calculus, if the y-axis and the x-axis have units like speed and time, in three-dimensional space, if the x, y, z axes have units associated with them, that volume under the curve has physical significance that can be interpreted, and you have to pay attention to the units of measurement on the XYZ axes to identify via them. You're just multiplying, so you identify by analyzing the units what that volume under the curve means.